Good day. This is MEG 224, Engineering Mechanics 2, Dynamics. Lecture 7, Part C, and the concluding part of Lecture 7. Planar Kinetics of a rigid body, force, mass, and acceleration. It can be found in Chapter 17 of Engineering Mechanics, Dynamics by R.C. Hibella. Lecture objective. The objective of this lecture is to look at the application of planar kinetic equation of motion to bodies undergoing translation, rotation about a fixed axis, and the general plane motion. General application of the equations of motion. In summary, three independent scalar equations can be written to describe the general plane motion of a symmetrical rigid body. That is, summation fx is equal to magx, summation fy is equal to magy, then summation mg is equal to ig alpha. These are for translational motion, while this one is for rotational motion. So if there's no rotation, this will drop off. So when applying these equations, always draw the free body diagram as shown in figure E in order to account for the terms involved in the summation fx, summation fy, and then summation mg, or summation mp. That is the moment, the summation of all the moments about p. In some problems, it may also be useful to draw the kinetic diagram for the body as shown in figure F. So this diagram graphically accounts for the terms. So this is summation magx, this is summation magy, then this ig alpha. So it is especially convenient when used to determine the components of mag and the moment of this component in the summation mkp, that is the sum of the moments, some of the kinetic moments about p. So equation of motion, translation. When the rigid body in figure A undergoes translation, all the particles of the body have the same acceleration. Furthermore, alpha is equal to 0, in which case the rotational equation of motion applied at point G reduces to the simplified form, namely summation G is equal to 0. Application of this and the force equation of motion will be discussed for each of the two types of translation. So, and then we have two types of translation. We have rectilinear translation, then we have curvilinear translation. Rectilinear translation. When a body is subjected to rectilinear translation, all the particles of the body travel along a parallel straight lines. The free body and the kinetic diagrams are shown in figure B. This is the free body diagram and this is the kinetic diagram. So since ig alpha is equal to 0, that is, there's no rotation, then only mag is shown in the kinetic diagram. So hence, the equation of motion, which apply in this case, become summation fx is equal to magx, then summation fy is equal to magy, then summation mg is equal to 0 because there's no rotation. So it is also possible to some moments about other points on or off the body, in which case the moment of mag must be taken into account. That is, how far is mag from that point you are looking at, and that point becomes the moment arm. So because when we want to find moment is force times perpendicular distance, and this is force. For example, if point A is chosen, which lies at a perpendicular distance d from the line of action of MAG, the following equation applies. So summation A is equal to summation MKA, summation which is equal to MAG times D. So because D is the moment arm. Here, the sum moment of external forces and coupled moments equals the moment of MAG about A. That is summation MK, which is the kinetic diagram. Curvilinear translation. When a rigid body is subjected to curvilinear translation, all the particles of the body travel along parallel curved paths. For analysis, it is convenient to use an inertial coordinate system having an origin which coincides with the body's mass center at the distance considered, and the axes are oriented in the normal and the tangential directions to the path of the motion as shown in figure C. So we have curvilinear motion. This is the tangential direction, and the normal is always directed towards the center of the curvature. So this is the free body diagram, while this is the kinetic diagram. So the three scalar equations of motions are there. Summation Fn, that is the sum of the forces in the normal direction, gives us this. Sum of the forces, or summation of all the forces in the tangential direction, is this. And then some of the moments, summation of moments about the mass center is 0 because there is no rotation. There is no rotation. So if moments are summed about the arbitrary point B, figure C, then it is necessary to account for the moment of these, of the two components, for the normal and the tangential forces about this point P. This is point B. So the moment will be E. Sorry, the moment arm is E. So from the kinetic diagram, H and E represents the perpendicular distances, moment arms, from B to the line of action of the components. So H is the distance of B from line of component of the normal force, while E is the moment arm from the line of action of tangential force. This is tangential force, and this is the normal force. So the required moment equation therefore becomes the summation of forces, summation of moments about point B is equal to, this is the tangential force times the moment arm, then the normal force times the moment arm. So equation of motion, rotation about a fixed axis. Consider the body shown in figure A, which is constrained to rotate in a vertical plane about a fixed axis to the page and passing through point O. So it's rotating like this. Instead of being hinged at the center, is being pinned or hinged at a point O, away from the center, or away from the mass center. So the angular velocity and the angular acceleration are caused by the external force and coupled moments acting on the body. So the external force F, and then these are the coupled moments that are acting on the body, which are producing the velocity as well as the angular velocity and angular acceleration. So because the body center of mass moves around a circular path, then the acceleration of this point is best represented by the tangential as well as the normal components. The normal is always directed towards the center of the curvature, while the tangential is always tangential to the path. So The tangential component of the acceleration has a magnitude of AG tangential, which is alpha r, and then must act in a direction which is consistent with the body's angular acceleration, alpha. So the component is always the magnitude of normal component of acceleration is omega square rg. This component is always directed from point G towards O, regardless of the rotational sense of omega. The free body and kinetic diagrams for the body are shown in figure B. This is figure B. This is the free body diagram showing all the forces and the moments that are acting on the body, while this is the kinetic diagram showing all the moments and the acting, the forces and the moments acting. So the two components, the tangential force and then the normal force, shown in the kinetic diagram are associated with the tangential and normal components of acceleration of the body's mass center. So the I alpha vector acts in the same direction as alpha and has a magnitude of Ig alpha, where Ig is the body's moment of inertia calculated about the axis, which is perpendicular to the page and pass through G. This is G, and that axis is called Z. So this equation, the equations of motion which apply to the body, can be written in the form summation Fn is equal to MAGN, which is M omega square Rg, and then summation Ft is M alpha Rg. You just have to add mass to your alpha, that is to your acceleration, the tangential acceleration, then it gives you tangential force. And then summation mg is equal to Ig alpha, that is the sum of all the external moments about G. The moment equation can be replaced by a moment summation about any arbitrary point P on or off the body, provided one accounts for the moment summation mkp, that is the sum of all the summation of all the moments, the summation of all the kinetic moments about point P, produced by Ig alpha, mat, and then the normal force about the point. So often it is convenient to sum moments about the pin at O in order to eliminate the unknown force. From the kinetic diagram, figure B requires that this summation O, that is moment of the summation of all the moments about O, will be equal to the summation of the kinetic moment about O. This will give us R G M A G T, that is the tangential moment, plus Ig. Note that the moment of MAG is not included here, since the line of action of the vector passes through the center. So there's no distance between this line of action and then the line of the line that connects O to G. So that R will be 0. So by multiplying it out, it will cancel itself. So AGT is RG alpha, or alpha R. A is alpha R. We write the above equation. We may rewrite the above equation as this, that summation, the total moment, that be the sum of all the moments about point O, is the moment of inertia of G of the mass center plus mr square times alpha. For the parallel axis theorem, I naught plus Ig is equal to md squared, and therefore the term in parentheses represents the moment of inertia of the body about the fixed axis of rotation about passing through O. Consequently, we can write the three equations of motion for the body as the sum of the forces in the normal direction is m omega square rg. The sum of the forces in the tangential direction is m alpha rg. And then the sum of or summation of all the moments about O is IO alpha. When using this equation, remember that IO alpha accounts for the moment of both the tangential and then the IG about point O, as shown here. So, in other words, summation MO, the summation of all the moments about point O is equal to the summation of all the kinetic moments about point O, which is equal to I naught alpha, as indicated in the equation above. Equation of motion, general plane motion. The rigid body shown in figure A is subjected to general plane motion caused by the externally applied force and coupled moment system. So this is the body. The free body and the kinetic diagrams for the body are shown in figure B. This is the free body and this is the kinetic diagram. So if an x and y inertial coordinate system is established as shown, the three equations, this is the three equations of motion are summation fx is equal to magx, summation fy is equal to magy, then summation g, that is the summation of all the moments about the mass center, is equal to ig alpha. So in some problems, it may be convenient to sum moments about a point P other than G in order to eliminate many unknown forces as possible and from the moment summation. When used in this more general case, the three equations of motion are summation fx is equal to magx, summation fy is equal to magy, and summation fp is equal to summation mp, that is the summation of all the moments about point P is the summation of all the kinetic moments about that same point P. Here, summation mkp represents the moment sum of ig alpha and mag or its components about point P determined by the data on the kinetic diagram. Thank you. So let's look at one example or tutorial. So at the instance shown in figure A, the 20 kilogram cylinder rod has an angular velocity of omega is equal to 5 radians per second. It said determine the angular acceleration and the horizontal and vertical components of reaction of the pin on the rod at this point. The rod this is the rod, and is made to be straight in the x direction, that's I or xi. Then is to rotate clockwise, then coming down. So the angular acceleration and the angular velocity is 5 radians per second. And we are asked to determine the angular acceleration. So solution. So let's look at the free body and the kinetic diagram that we'll be chatting about. So this is the free body diagram, and this is the kinetic diagram. At point O, we have two reactions. Because the object is in a circular motion, we will have the tangential tangential acceleration and tangential force. Then we have the normal acceleration, which is directed towards the center of the curvature, while this component is tangential to the curvature itself. So, as shown on the kinetic diagram, figure B, point G moves around a circular path, and so it has two components of acceleration. It's important that the tangential acceleration, AT, is equal to this, acts downward, since it must be in accordance with the rotational sense of alpha. So since the object is rotating downwards, then it is important that this AT acts downward. So in the same direction as alpha and omega. So the three equations, the three unknown equations are ON, OT, and then the alpha, which is the angular acceleration. So equation of motion. We have established that summation Fn is this m omega square Rg. The point of action of G from the pin is 1.5 meters. That's the moment. We want to find the moment. Then omega is 5, and the mass is 20 kg. So then the tangential force is this m alpha Rg. So this OT also is in that category. So, but the mass is this. This is mass times acceleration, because the acceleration is due to gravity. This mg is equal to mass 20 times alpha, then times 1.5. Summation mg is equal to ig alpha. So here we sum all the moments together. This is the moment, the tangential moment, and then the moment established here, then it's equal to ig alpha. So this is ig, is alpha. So when we solve these equations simultaneously, we discover that the normal acceleration at point O is, sorry, the normal force at point O is 750 newtons. The tangential is 19.05. Then the angular acceleration is 5.90. So thank you. That's the end of part C and end of lecture 7. So please do not forget to share my videos, like my videos, subscribe if you have not subscribed already, share, then press notification bell for new videos if you have not done that. Then if you are one of my university students, please subscribe with your real name. Thank you.